All right, let's see. All right, so I think I'm recording on twice, just in case. All right, so let's start. So I was saying, where are we in the course? So Project Zero is over. Hopefully this project gave you some skills in GDB, and also you understood few things. You understood how Pintos is built, and you understood a little bit how the bootstrapping works. So this week what you're going to do is you're going to look at the threads. So how to manage the threads and how to schedule those threads. Okay, so basically stuff that we have talked about last week and that we're going to talk also this week. This project, I have to tell you, it's big. You have 3 weeks to do it, and what I will recommend is like there are 3 parts. First part is you have to transform the current threads that are using that are doing I/O in a pooling way. Okay, meaning the old way that you did in B58, which is you basically wait for the I/O to be ready. Okay, this is not good. I mean, you cannot have multi-threading if you do that. The idea is like to switch to interrupts. Okay, you do an I/O request, and basically you shut down. Basically, you put yourself in a blocked queue until there is an interrupt from the I/O. Right. So that's the idea. That will be for week 1. So you have to, I believe, you have to finish that by the end of this week. The programs that we're considering is just an alarm clock, okay? But the idea is like to have multiple alarm clock going on in parallel. On the second week, you're going to touch a little bit the scheduling, okay? And what you're going to implement is priority scheduling. Right now, there's a round robin already implemented. You move to actually some priority scheduling. So that is going to be week 2, and then week 3, you will see there is advanced scheduling, which is actually the multi-level feedback queue that we saw also last week. Okay, so 3 weeks to do it. Every week there is a deliverable. My advice is like really stay on track and try to finish one part every week. Otherwise, it's going to be complicated. Okay. There's a question: do we build on Project Zero? No, I wrote that on Piazza. You can start fresh. Okay, so all the monitor, the monitor that you build for Project Zero, it doesn't matter here. Okay, so feel free to start fresh. This is not going to be the case for Project 2, 3, and 4, right? They're going to build on top of each other. But at least for Project 1, you can start fresh. Okay, are the solution for Project Zero be available? I don't know yet, and I don't think so. Okay. But I'm always willing to discuss it privately if you want. Okay, so that's why. So the TA are gonna go through some important aspects of Project 1. Okay, and I provide them with slides, and the slides are already on the course website. If you go to the project page, you will see that I've added some slides next to the Project 1. So I don't think the TA are gonna cover everything this week. So I told them, if you don't finish, that's okay. Take your time, and then you will finish it next week. But at least I want them to talk about, to introduce the threads, to introduce the difference between pulling and interrupt, and a little bit of scheduling, so that at least you have enough to go through. Okay. All right. So. Okay, there's a question here. Do you choose one person's repo for submission? We are in the team. No, go through GitHub Classroom, and there actually you have to basically create some kind of a repo or join an existing team. Okay, so if you are in the team, you should all join the same repo. So try to follow the guideline, and again, do that early. By the way, you should push almost every day. Okay, don't wait for the last minute. Also, something I wanted to say. Again, Pintos, many universities are using it. Many universities have used the same assignment. Probably there are some solutions out there, but actually, it's not just probably, it's like there are some solutions out there. Don't even look at them, okay? For sure, if you look at them, you're going to be in serious trouble. I'm going to run plagiarism detection tools on all your submissions, plus all the stuff I found online, okay? So on a code as big as an OS, chances are that if you even look at the code or copy the code, similarities will show, evidently. And any kind of suspicious case will be reported to the dean's office directly. Okay? So please don't do that. Don't even look at it just to get an inspiration. It doesn't work. Take your time, read the documentation, work on it. It's definitely feasible. But again, don't start late. That's where you're going to be in trouble. All right. Also, this week, office hours, the TA have office hours. I have office hours tomorrow. So feel free to actually drop by. First half an hour, it's going to be general questions, public questions. I'm going to answer them all live. And then second half hour, I'm just going to answer a question privately. Okay? All right. So let's start with the topic of the day. So this week, we're going to talk about threads and synchronization. And again, this is going to be useful for the project one. So here, a quick recap about what we saw last time. So last time we saw the concept of process. Okay? And a process basically is defined by its process control block, which is a data structure recording all kind of information about the process, whether the process is running or waiting or actually ready to be executing. The address space layout, okay, we're going to see that a bit more when we talk about virtual memory, but also the execution context, program counter, stack pointer, all the registers and so on, and some resources, open files and so on and so forth, although this is also something we're going to see later in the semester. Okay. The idea here is to have different processes that they don't interfere with each other. So each of them has their own address space and so on. And the only way they can collaborate is basically to use inter-process communications, signals, pipes that you saw in BO9. Okay? But this kind of multiprocessing has a cost. Okay, so if I go back to an example I used last week, which is the web server, the idea was as follows, right? You have a web server, the web server receives a lot of requests. Every request, you're going to create some kind of a child process to handle that request. Okay, the idea here is to take advantage of multiprocessing to process all of these requests in parallel. Okay, so if you do that in the way we did it last week, you're going to use a fork to create a child process, meaning for every new request, what you're going to do is create a new PCB. You're going to copy the address space and the resources, and you will have the OS basically executing those child process one by one by switching the context. Okay, and here it's not in the circle, but now if we want also the child process to communicate back to the parent process, we need to use signals and pipes. All of that is very costly, actually. Okay, so it's good because the process is not going to interfere with each other. Okay, every time we copy the context and the stack and so on. But creating a process is costly. Switching the entire context is also costly, and communication as well. So here, it's good to have different process, separate. But sometimes what you want is within the same application, you would like to have some kind of cooperating processes. Okay, meaning you want to have child process that kind of they talk to each other, they cooperate, and they share the same code, the same data, they share the same resources, they share the same privilege, basically. Okay, while of course they have different execution contexts, right? The idea is to have some kind of a multi-processing, kind of lightweight, okay, at the application level. So we need to rethink about process, and the idea here is like, okay, let's separate the process, okay, which is recording all the address space, privilege, resources, and so on, from the execution state, which is the program counter, the stack pointer, and the registers. Okay, and if we do that, what you obtain is the difference between a process and a thread. So most of the modern operating systems, they have this concept of process and threads. Okay, the thread defines a sequential execution stream within a process. Okay, you can think about it as in some kind of an execution box, while the process actually defines everything that this thread can access, right? So the address space, attribute, all the files open, and so on and so forth. So this is actually a good abstraction from concurrency, right? And the idea here is that the threads becomes a unit of execution, meaning something that you're going to schedule now. Okay, so last week we were scheduling processes, but now we're going to schedule threads. Okay, and the process is just going to be some kind of a container in which threads execute. Okay, so the idea here, and that's showing here in the drawing. Okay, what we had last week, you can think about it as a single threaded process. Okay, we have one process, one kind of unit of execution. Now you have actually multi-threaded process. Okay, meaning within one process you can have multiple threads. Okay, and of course you can have multiple processes, right? Within the same process, the threads, they share some data. Okay, so that's really the idea. And again, you know, Windows, Linux, Mac, you name them, they all use this kind of abstraction. So how does it work? Well, the idea here is like, you know, if we take a look at the picture that I have about the process from last week, you know, a process, it's defined basically by the code, some data, the stack, and the heap, right? That was the execution context of a process. Okay, and all of that is recorded in the PCB. But now, because you can have multiple threads within the same process, and they share actually the same code and the same data, meaning the heap here and the static data, but they represent different kind of execution thread. Okay, so here, that's why you have actually multiple stacks. Okay, so here, for example, you have like 3 threads within the same process. Okay, so now if we think about of our web server, what you want is, you don't want to create child process to handle requests, because that's actually costly, but you can use threads, because actually now they're going to use the same data, which is here the socket. They're going to collaborate. They can send back the result to the main thread, if you like, and so on and so forth, without actually having this kind of heavy kind of process thing. So the idea now is like, it's just become like now, rather than doing a fork, you're going to do some kind of a thread fork. Okay, and same thing, you're going to handle the request separately. Okay, it doesn't change the structure, but it's just like, you know, instead of creating a child process, we're going to create this lightweight kind of thread. So what's the benefits? The benefit of that is responsiveness. Imagine any application. So for example, imagine your word processor. You know, as you type and you format your document, in the background, sometimes there is something that there is actually another thread that records that save the document for you as you type, right? You don't have to click the button save. That's one example, right? You have 2 threads here, one that is basically listening to your keyboard inputs and so on, and updating the document on the screen, but there is another thread actually recording that. Okay, so it's good to have that, because if you have different process, you know, they wouldn't reshare the file itself that you are writing, so it would be very, very costly. And every time you need to switch process, you know, as you're not typing, it's recording, and so on and so forth. That's not really efficient. Resource sharing, I told you that, right? So basically, the threads can share data. So in my word processing example, you know, you share actually what you are typing. Economy of time and space. Okay, time, because you don't have to create all this PCB and switch the entire context and so on. Okay, you still need to switch the registers and the stack, right? But not the entire memory space. And also space, because you don't have to record all this stuff, right? So, and also it's scalable in a multiprocessor architecture, right? So the idea here is like, I told you, right? Once we have a multiprocessor, what you can do is like, last week, we could actually put one process on each of these processors. But now it's even better, right? Because now an application can have multiple threads, meaning for the same application, we can have different threads running on different core. Meaning you can have one application that is actually multi-threaded and taking advantage of the multiprocessor architecture, which wasn't the case when we had only process before. Okay, so so that's why actually threads are very common in OSs. how to implement those threads? There are three ways, but really, like among these three ways, one of them is implemented by all the OSs, and the second one, so it's going to be the first one, the one-to-one model, implemented by Windows, Linux, Mac, and so on. And the second one, the many-to-one, it's implemented by some specific applications, and also it's offered as a library. You will see. The last one, the hybrid model, although it's a good idea, it's actually no longer implemented in practice. So let's go through that. The one-to-one model is as follows, right? So now the kernel is going to manage and schedule threads. Last week, we were managing and scheduling processes. Now it's no longer, still we have to manage the process, but when it comes to actually schedule those processes, we're not going to schedule process anymore, but schedule threads. At least when you start a process, it has one thread, okay, what we call the main thread, and within that process, you can create multiple threads. Okay, so that's on Windows, it's called threads. On Unix system, actually Mac, Linux, and so on, it's called pthread. There are different pthreads. There are pthreads scope system, and there's pthread user mode. And then Solaris as well. Solaris are a big Unix server. In that case, operations are managed by the kernel, which is good for scheduling, but it's bad for speed because now everything has to go to the kernel. Okay, so it's still faster than process, but still there's a little bit of overhead. Quickly, something that you will encounter if you program in C. How do you create threads? Well, there is a function called thread create. Okay, you pass a function that you want to execute, some kind of handler, and that's it. So this is going to create a thread control block, okay, which is a lot lightweight than just the PCB. It's going to allocate the stack, put the function, the args, and so on the stack, and then put the thread on the ready list. Because here this is like native threads, right? Kernel threads. But that's it, right? We now have to switch the stack, the memory map, and so on. Of course, you can destroy a thread, and you can wait for a thread to exit, right? A little bit like the wait for a process. So another one that is also popular is to have threads at the level of the application. Okay, meaning now the kernel is not involved. It's really like, the kernel is going to give the processing time to some kind of a thread or process, it doesn't matter, right? And there you're actually going to manage all your own scheduling and all your process at the application layer, right? So it's like kind of like, you push that to the application itself rather than the kernel. So in that case, what you do is like you delegate to a library. And this library exists actually on Linux, Mac, and all the Unix system. It's called pthread scope process. So you see here actually on Linux and Mac, you can actually choose whether you want to run thread at the user level or threads at the kernel level. So it's very flexible. But also, if you think about it, Java threads are like that, right? So if you start a Java virtual machine, it has its own process and its own main thread and so on. But then on top of that, you can create Java threads. And these Java threads are going to be kind of application type of threads. In that case, the kernel is not involved, so it's very lightweight, very fast, right? So you do everything at the application layer. But at the same time, if one of the thread is blocked, it might actually tell the OS, okay, it's waiting for an I/O, so it's going to block the process in a way, or it's going to block the main thread, the kernel thread. And if it does that, well, all of them are blocked, right? So here in the drawings, if this one is blocked because here somehow we are doing an I/O and we yield the scheduling, well, this might be blocked. Okay, so it depends how you manage it, but most of the time it can happen. And also, you cannot schedule it on multiple cores, right? Because this is actually what's going to be scheduled on the core. Okay, not this stuff. This stuff is kind of like you are doing it artificially. So let's see. I see some questions. I'm going to answer that, but let me finish with the last implementation, which is some kind of hybrid approach. What's the hybrid approach? Imagine you have some kind of a pool of kernel threads, okay, that that you're going to schedule and so on, and then you have many user threads. Usually, you have more user thread than you have kernel thread, right? And then you try basically to allocate every user thread to a kernel thread. Okay, so that's why we call it like NM multiplexing threading usually. This is how it works on the old Solaris system, but actually it looks like a good idea, but it's not. It's actually more efficient to go back to basically that, to the one-to-one model, and that's why Solaris now, the new Solaris version, they switched to this one-on-one model, okay, with the LWP, lightweight processes. So out of the three models, the last one, the hybrid one, is not very used. Okay, the first one is the one that most of the OSs implement by default, and this one, it's made available sometimes to the user through a library, or sometimes like special programs like Java. Here I'm talking about Java threads, but maybe actually all kind of as soon as you have virtual machines or a language interpreter and so on, they enable like threading like that. Okay, so let's see. So let me move to some questions here. Is thread create part of Pintos? Yes. So on Pintos, you will have to create threads. So it's actually already there. I mean, look at the code. So you're going to create threads and you're going to schedule them. Yeah. If there is one kernel thread per process, how is the kernel not involved? You're right. The kernel is somehow involved, right? I mean, here, if I go back here, what the kernel is going to do is is going to schedule this one, right? So that's what the OS is seeing. So here, if you see multiple process, it's going to have, every process will have one kernel thread, and the OS is going to basically schedule all of these kernel threads. But what happened above that, at the application layer, the kernel doesn't see it, right? The idea is the processor is going to give kind of the CPU time to this kernel thread, and then after that you will have some kind of a library that decides, oh wait, I'm going to execute that branch, or I'm going to execute that branch, or even, while my CPU time quantum, that, I don't know, assuming it's 100 milliseconds, I'm going to do, 20 milliseconds for each of the branch, and I'm going to really alternate fast, okay? But again, this is basically, the library does that, right? It's like kind of, imagine you writing this kind of library where, you are able to actually to switch between programs, between, kind of execution context, okay? That's the idea. Why is hybrid thread bad? It's not bad, but it's kind of hard to, manage. Sometimes you see that. Every time you're going to see the following. Actually, sometimes you see these kind of things. For example, I think if you look at Node.js, they do this kind of hybrid threading. The idea is the following. You're going to tell, okay, I'm going to run my application, and my application will have that many kernel threads. Okay? And so you're going to create the pool here. And after that, this application, because it's a language interpreter or because it's a virtual machine or something like this, it's going to create multiple instances of user threads. And automatically, you will have the application or the VM, if you want, the virtualizer, or the language interpreter, scheduling those threads on all the kernel threads that are available and try to maximize actually the execution. So it's not bad, but it's big machinery. That you have to do it right, but at the end of the day, if you can rely directly on this kind of model, okay, and you basically you can create a program where you can create threads and so on. You don't have any restriction on the system. This is actually even more efficient, right? Every time you need a new some kind of every time you need a thread, you just create a kernel thread. That's the idea. Okay, can you explain the difference between threads and process? Okay, process, again, we created the concept of process to isolate the execution of a program from another, okay, from each other. So to avoid interfering, actually, we reserve some kind of a memory space. We reserve, when they when they create data, when they create open files, and so on and so forth. There is some kind of a separation between two running processes. Okay, that's what we did last week. And we did that by design. Okay, you don't want to have a process on your machine interfering with another one. Okay, reading data and so on. That would be bad. So that's why we invented the concept of process. But every time you want to achieve kind of multi-threading, okay, or multi-processing, I mean, every time you want to achieve some kind of concurrency, the only choice you have is to spawn a child thread. Okay. This has a cost because, again, you're going to reserve some kind of a memory space. You're going to recreate the PCB. You're going to recreate everything. Okay, and you have to do context switching. I talked about scheduling last week. You have to switch between those processes. All of that has a cost. The idea here is to have something kind of more lightweight. Okay, it's not a replacement. So you have something more lightweight where actually, even within a process, you have actually different context of execution as threads, right? And you can have, for example, this one, thread 1, waiting for an IO, but this one, it's still running, okay? Although they are part of the same process, meaning they are part of the same application. And they share data, they share the code, of course, they share a bunch of things. They share open file and stuff like that. So here, for example, two threads cooperating to each other. Imagine, one is reading data and the other one is kind of like writing those data. They can pass the data around directly in memory. As opposed to process, they need to communicate to pipes and so on, which is costly. Okay, so that's why it's some kind of you have to see threads as a lightweight process. Okay, but now at the level of the OS, when it comes to actually managing and scaling threads, what the kernel sees is a bunch of kernel threads, and it tries to give them CPU time to each other, right? But maybe two of them, here for example, maybe these two are from the same process. Maybe this one is another process, and the fourth one is also another process, right? So, which one-to-one bad for speed? Here I'd say bad for speed because here, you have the chance to do that, but if you write some kind of a C code doing multi-threading, you have to call some syscall because, again, all the creation and so on, all the management is done by the kernel. So every time you want to create a new thread and you want to schedule it and so on and so forth, you have to talk to the kernel. So here, imagine the kernel has hundreds of processes going on, and each process has maybe 2 or 3 threads. And creating threads on the fly. Now, all of these requests has to go to the kernel. So there's some kind of a bottleneck at the kernel level, right? You will understand that actually with Pintos. So it's bad for speed, but at the same time, it's not that bad because we are doing it, right? Windows, Linux, and so on, they're using that. It's just that I'm saying it's bad for speed as opposed to the second model here, which is very lightweight. It's even more lightweight than kernel thread. Okay, this is actually even faster. Okay, but it has some limitations. There is one kernel process. Well, actually, now you have, yes, there is one kernel process. We saw that last week. If I show up the thing on your Mac, my Mac, there is like kernel. Actually, let me show you. If I show you, no, that's not what I want. I want this utilities, activity monitor. So you see here the kernel task, which is my kernel actually, because this is PID 0. Okay, so that's the first one. So that's a process, but within that process, as you can see, I have 247 threads. That's all my kernel threads. Okay, actually the others are also kernel threads, but these ones are specific threads only for the kernel process. Okay, so usually what they do is like they manage input output. They do all kind of things. Okay, but here, for example, this application here, that's another process, and it has again 15 threads. And the scheduler here is trying to give CPU time to all of these threads. Okay, now the scheduler doesn't see process; it just see a bunch of threads. Okay, so it tries to give CPU time, and here you can see, my kernel has got 10 hours of CPU time since the last boot. Okay. All right. No, that's not the activity monitor. Okay. All right, let's continue. So that's in a nutshell. So that's why when you're going to look at Pintos, you don't have processes yet, okay? Because in Pintos it's weird. We're going to start first with kernel threads, okay? And the kernel threads, they all share the same scope and so on. And then actually it's going to be project 2 when we are going to add the extra process layer, okay? But why did I start actually to explain process? Because I had to actually relate to what you have seen in BO9. So it was kind of easier for me to ease you into talking about process because you knew about process from BO9, you knew about fork and so on. But then I had to introduce a thread like that. So that's why. But at first, the first assignment is only going to be about kernel threads, and then you're going to add the process layer for project 2. Okay, so now we have threads, and they can collaborate. Great. So here, what you can do is one application can spawn, create many threads. And here you can have, imagine one application having a ping thread and a pong thread, okay? And this is basically 2 infinite loops printing ping. One is printing ping, the other one pong. So here, because it's multi-threaded, this doesn't kind of while this is executing, this is not just never going to finish, right? Here, there's going to be the scheduler who is going to alternate between ping thread and pong thread, right? It's going to try to give CPU time equally. Meaning we're going to have an alternation of printing ping and pong. Now, is it going to be exactly ping pong, ping pong, ping pong? No, okay? Because it depends. And this is where here it's going to be not predictable. Sometimes you're going to have ping, 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 pong, pong, ping, ping again, and so on. And you might see actually all kind of execution, right? And it's not predictable at all, right? So it's one of the problems here, and that's what we're going to try to solve. The problem is a bit bigger, and let me start first with some kind of a very abstract problem. Okay, imagine 2 people, okay, living in the same home, and one of them, Alice, she looks into the fridge, open the door, and find there is no milk, and she needs milk. So what does she do? Well, she go to the store, okay, she arrive at the store at some point, she buys milk, come back home, and then put it in the fridge. Okay, but imagine at the same time, while actually Alice was away, Bob did exactly the same thing. Okay, so imagine actually there are 2 threads doing the same thing. Okay, meaning you look in the fridge, out of milk, okay, fine, I go to the store, I arrive at the store, I buy milk, and then I arrive at home, there is already milk in the fridge. Okay, well, is that a problem? Maybe. Okay, maybe that's too much milk, and it's gonna go bad. So here we have, you see, it's easy to see that we have a synchronization problem, right? Alice and Bob need to talk to each other to say, hey, we are out of milk, let me do my job of buying milk, and after that you can do whatever you want. Okay, so that's kind of the idea here. Beyond milk, let's talk about just programs written in C. Imagine 2 very, very simple threads. Okay, so if they are threads, part of the same process, meaning they share a variable. So here, assuming that thread 1 and thread 2 are, belong to the same process, they share a variable x here. And at first, before these threads are created, we initialize this variable to 0. And then we create those threads, and we call the function foo and bar, and then we wait for the 2 to finish. Okay, what's the value of x after 1 and 2? Okay, after both of them are finished. Here, you might have this intuition that, wait a second, some answers here, 0, yeah, that's the first intuition we have, right? Why? Because if it's thread 1 that goes first, it's going to increment this variable. And then if it's thread 2 that goes there, it's going to decrement the variable. So it's going to be +1, -1. Or you might think about it as thread 2 goes first, do -1, and then thread 1 goes after, and then do +1, meaning it's going to be 0. Okay? So intuitively, you might say, okay, it doesn't matter here. After thread 1 and thread 2, it's going to be 0. And it's wrong, as some of you here are guessing. Why is it wrong? Well, this is C code. We have to look down at the instruction level, meaning at the CPU level, where, there we talk assembly code. And when you compile a code like this, just like this x++, I'm not going to even talk about the function here, sorry, but just this x++ and x minus, here it's going to be at least, okay, compiled into 3 instructions, even more sometimes, okay, depends. But there's going to be 3 instructions. One is, it's going to load the value, because this value is stored in memory, and first we have to actually load that into a register. We're going to increment this value, okay, directly in the register, and then we're going to put this value back into memory, right? 3 steps, okay? We take the value, we read the value from memory, we add +1, and then we put it back. And of course, same thing when you decrement. So here, what can happen? Well, again, if these 2 threads are scheduled using the scheduler, what we said last week is still true, right? At some point, this is going to be, this program is going to be executed, this thread, and then there's going to be a timer, a timeout. The timeout is going to be an interrupt. As soon as we have the interrupt, we stop what we're doing. We stop what we're doing, and we are switching to another one, okay? And we resume it. So here, what can happen? Where are we going to break? Are we going to break after, before that, here in between, or after this? It's hard to tell. It's actually unpredictable. You run it 10 times, it's going to be different. Meaning here, you can have all kinds of executions with kind of weird outcome. Okay? So let's look at the first one, which is kind of like, what I told you before, which is first thread 1 goes, and after this one, there's kind of a context switch, and then we go to thread 2. In that case, we read in memory +1, put it back in memory, and then process 2, read in memory, decrement, put it back in memory. Here it's going to be 0. Okay, and it's going to be 0, by the way, even if thread 2 actually goes first. But here, let's imagine a second scenario, right? First, thread 1 load X, and then what? And then interrupt, timeout. And then thread 2 goes there, and then also read X. It's the same value of X, right? X equals 0. And then here we increment the register, and then again interrupt, right? And then this one also is going to increment this register, store X and store X. What happened here? Well, X is equal to -1. Why? Because it's the last one who is kind of has the last word. Okay, it's going to be the decrement one. Okay, because here it's going to overwrite the value that was written in memory, by this one. You can have again another scenario here, which is, it's kind of the same, but at the end, it's actually thread 1 who is the last one to store the value X. In that case, it's going to be equal to 1. And again, I'm giving you 3 scenarios here, but you can have all kind of scenarios. Okay, you can imagine all kind of things here, many possible scenarios, and the outcome is always going to be either 0, -1, or 1, and it's not predictable. Okay, so yes, on the chat here, Amo said it. It's like it's not atomic. What does it mean, not atomic? Here, this X++ is not done atomically. Okay, instructions at the level of CPU, yes, they are done atomically, right? But not at the kind of C++ level. Okay, you don't know how it's going to be there. Does each one of these instructions have their own interrupt? Instructions don't have interrupt. It's not the way it works. Okay, what's there is, remember, here, the OS is going to say, okay, let's execute that one. And the CPU is going to execute it until something happens. What happened? Until there is an interrupt. Because the OS has set up an interrupt saying, hey, can you give me a ring in 100 milliseconds? And as soon as you receive the interrupt, it's going to be the interrupt handler who is going to be called. Okay, and again, we saw that last week. The interrupt handler is what it's going to do is going to stop the execution. I mean, the execution has already stopped, right? Once we execute the handler, it's going to stop. But it's basically going to record the stack, the registers, the program counter, and then it's going to switch to another thread. And meaning it's going to put again the stack, the program counter, and so on of this thread, and then run it until there is another interrupt, right? So, I mean, there is no interrupt at the level of functions. Okay, interrupt, you can see that as some kind of an input-output. Okay, but every time the CPU receives an interrupt, it stops right away what it's doing and then call the interrupt handler from the table. It can be other value too, right? So Sakina, you asked a question. No, in that case, because here I don't have a loop, right? If I had a loop here, yes, you're right. It can be all kind of values. Okay, it's not bounded. But here, because I do it only once, I don't think it can be something else than -1, 1, or 0. Sorry, -1, 1, yeah, or 0, yeah. But if I have a while loop, yes. Yes, most function code, I mean, every instruction in a language is unlikely being atomic. Yeah. Every kind of like lines of code, even the simplest one, like an X++, sometimes most of the time, it compiles into multiple assembly instructions. Every function code is not atomic. Yeah, same thing. It's the function at the level of CPU. There is no such thing as function, right? It's just like they do jumps, they put stuff in the stack, and that's it, right? So even there, functions don't really exist. Yeah, you thought it was a loop, but it's a good point anyway. So if you have a loop, yeah, it can be all kind of values. All right, let's move on. So where I was. So when you have this kind of behavior, which is actually you cannot predict the behavior of your system because you don't know in which order things are going to be executed. Okay, and you can do it 100 times. It's going to be different. Or maybe actually you're going to do it 100 times. 99% of the time it's going to be the one way, and then the 100 ones you don't know why it's going to be different. Okay, so in that case, what you have is something called a race condition. Okay, we're going to talk about that even more next week, but this is actually a really hard bug. First of all, it's a bug hard to catch. Why? Because sometimes you cannot even test. Because you're going to test it, maybe the race condition, you're not going to trigger it. Okay, because the execution is actually going to be fine. And then one day, okay, or on one other machine you don't know, suddenly it's going to be different. Okay, and this non-determinism is usually in most cases not desirable. You don't want to have that. Okay, so and sometimes if you have that, it can have actually drastic consequences. Okay, we're going to talk about next week about some famous accident because of that, and life of people were involved. So here you don't want to have that. So what's the solution to that? Well, you need to avoid race conditions. You need to basically synchronize your threads to make sure that you control the sequencing of execution. All right, some questions here. So for execution scenario 2, the brute thread starts. Okay. Okay. Again, it's not the red process to send an interrupt, right? I wouldn't phrase it like that. It's like, the CPU somehow is interrupted because the OS has, that's how the OS is configured. Every 100 milliseconds, there is an interrupt going on, and the interrupt handler, basically what it's going to do is going to call the scheduler and move to and switch the context, move to another thread. Okay. But why does it go back to the brute thread before the red thread? Well, because that's how the scheduling works, right? So we saw it last time. It's going to give you 100 milliseconds. Okay, maybe what you're going to say is the following here. Okay, this instruction here, load X, is not it's not going to take 100 milliseconds. It's going to take maybe a millisecond, right? So in a one-time quantum, of course you're going to execute a bunch of instructions. Here, I want you to keep kind of the example minimal, okay? But it's really the same idea. I mean, it can happen anywhere in between, okay? And you cannot predict it, okay? As soon as you have an interrupt, it's going to stop what you're doing. This interrupt can happen anywhere, okay? But I agree with you here. My example is a bit artificial to basically switch one instruction after the other, right? That will be a very, very short CPU time quantum, okay? Not efficient. How does multi-threading work on a single core? It's exactly the same that we talked about last week, okay? This doesn't change. All the stuff I talk about scheduling processes, you can apply it to scheduling threads. It's exactly the same thing. So it works exactly the same. So go back to the previous lecture. If threads share data, wouldn't the value of X stay the same for both threads? But again, what does it mean to share data? By sharing data, you mean you share memory space. Okay, and that's what you do here, right? They share the memory space. When you do load X here, you read from memory. And another process is also going to do that. Okay, and you're going to store it in the register, but the register is going to be different because every time you switch process, what you increment and decrement is the register. That's really important. So here, when you're going to switch context, you're going to replace the value of the register, and that's the problem. Okay, the problem is, like, you know, if we were able to actually do that's actually a good comment. If we had an instruction that is able to actually do +1 directly on a piece of memory, okay, in an atomic way, we wouldn't have a problem, or at least not in this example here, okay? But that's not how it works. The single core, but again, you know, I mean, scheduling and multi-threading and so on has been invented for single core. I mean, this has been invented in the 70s, okay, this stuff, and we had only one core. But the idea is, like, you know, you have to go back to lecture 0 or lecture 1, where I say basically, why do we do this multi-threading? It's because it's actually good to actually run multiple threads, okay, let's use threads here at the same time, because all these threads are going to do input-output, and then to give equal time, so that from the user perspective, it looks like everything is going in parallel, okay? But I mean, of course, at the low level, it doesn't. If you have now multi-core, it's even better, right? You just have several cores, so when you schedule them, you don't have only one core to actually provision, but 4. Okay, so it's kind of the same thing. But again, multi-threading is very good for one core CPU. Okay, we have been doing it for like 40 years now, 50 almost. All right. Yeah. So from the processor's perspective, I mean, I would say from the OS perspective now, yes, I told you, right? Now that we have threads and kernel threads, we are not going to schedule process. We are going to schedule threads. Okay, we have all these threads, and we're going to try to give equal time to each other. But then again, everything I said last week, it's still true. Okay, it works exactly the same. All right, so let's move on. So you don't want to have this race condition. So a good thing to do is to identify when can I have a race condition. And for that, what you need to do is, like, you need to find in the code something we call a critical section. Meaning it's a piece of code that, you know, if there is some kind of an interrupt, meaning if there is a context switch in that place, we're going to have a race condition. Okay, so we are looking for, what we say is, we want to have mutual exclusion between two threads to basically synchronize access to shared resources. When two threads are going to access the same resource, okay, take again the example of the fridge, okay, and the milk. You want to actually say, okay, I'm going to get the resource, let me finish what I'm doing, and then after that you can go, right? It's again some kind of concurrent access to a resource. And we call that a critical section, okay? And the idea is, like, only one thread at a time can go in this critical section, okay? All threads are forced to wait, okay, before to entering with this critical section. And then when a thread leaves, another one take a place. So here, I'm going to move away from my plus example, but this one is a very classical one. You find it in every book. I mean, when I was a student, when I learned concurrency, I saw this example as well. Imagine you have a withdraw program, okay? So you're a bank and you can withdraw money. Okay, so you have the account, the amount, and what you do here is the following, right? First, you get the balance, okay? For that, you have a function. You get the account balance, then you update the balance, okay? You remove the amount, and then you kind of update the balance, right? And it's kind of like, it looks like my program where, I load something from memory, I modify it, and then I put it back, right? So, but it's more like kind of maybe relatable example. Imagine you do that, and imagine, you withdraw money from the ATM, or you withdraw money at the same time, so some payment is kicking in on your bank, right? And you have two threads going on at the same time. You have two payments going on, right? And that happens actually in real life, right? So here you understand that, if we had the problem that we had before, well, you might have a problem with your balance. Actually, this is going to be in your favor, right? Something is not going to register, and maybe one payment is not going to work. So that's good for you, maybe bad for the bank. Free money, exactly. So here we have something we call a critical section. So it would be good that, these three instructions, when one thread execute them, no other thread can do it, right? There is some kind of a stop here that says, okay, only one thread at a time do that. Once this is done, okay, fine, you can enter, right? So I'm going back to my slide before. Only one thread at a time can execute the critical section. All the other threads are forced to wait, okay, before entering. And then when a thread leaves a critical section, another one can enter, right? So here we're going to say, okay, in our example, that's our critical section here. So there are some kind of vocabulary that is around this kind of problem. So we talk about mutual exclusion. So if one thread is in the critical section, there is no other thread in that critical section, only one thread at a time. And we call that a safety property. Okay, nothing bad happen. Okay, you make sure that you are not going to have this kind of race condition. Progress. If there is one thread in the critical section, okay, it prevents all the other threads from entering, of course. But eventually, we need to give some kind of assurance that it's going to leave it. If it doesn't, that's bad, right? Imagine here you have an infinite loop, and then all the threads are blocked, all your payments are blocked. Okay, which might be good actually, but you might not withdraw money from the ATM. So there's kind of progress, right? Once you enter a critical section, you do something and then you leave. There's something called bounded waiting, no starvation. So now you can understand, I talk about starvation when I was talking about scheduling process. It's kind of the same idea here. Right? You have multiple threads that want to enter a critical section, and we need to make sure that, all of them are going to get into this critical section, right? So there's not one that is, always somebody is going to kind of like, move into the critical section, and one thread is never going to get it, right? So we call that some kind of a liveness property. I mean, these two, progress and bounded waiting, the fact that, imagine the queue is moving for the critical section, and at some point, you will get into the critical section. That's a liveness, which is something good happen eventually. Okay. And then of course, performance, the overhead of entering and exiting a critical section is small compared to the work that you have to do, right? Imagine if, you put something here to protect this section, and, it takes like, I don't know how many instructions compared to what you do, it's maybe not efficient, okay? But again, if it works, as long as you have safety and liveness, okay, you have done the right thing. Okay, so there are many mechanisms to build to do that. We're going to see two of them today. Okay, I hope we're going to have time. Locks and semaphores, because you're going to actually play with semaphores. I mean, every OS gives you access to semaphores. Not really lock, but we're going to look at lock because it's a primitive. It's the first idea. Actually, it's the first intuition we have, and actually locks are used to implement semaphores. And then monitors, but we're going to see monitors next week, I think. So what's a lock? A lock is an object in memory that provides two operations. One is called acquire, and the other one is release. Okay, imagine the following. To be able to go into the critical section, imagine my critical section is a room. Okay, and what you need is a key. Okay, a key to the lock, and only one person will get this key. Okay, so at first the OS is going to give that key to the first person. The person go into the room, do the business, go out, and unlock and give the key to somebody else. That's the same idea. You have some kind of a key or token. So here you acquire the key, the token, okay? And if it's not available, you're gonna wait. You wait until it's free. Once it's free, okay, then fine, you enter the critical section. So acquire will kind of like, stop you. It's gonna block you. And then you have release. Release, at some point you do your business and then you have to release that lock. You have to give it to somebody else, okay? And what we say usually, like, you wake up another person, okay? It's like, hey, wake up, that's your turn, here's the key. So a thread, you understand that when it's going to process a critical section, okay, like my Week3 example here, at first it's going to acquire the lock and then do something and then release the lock. What we do in between, we call that holding the lock. Okay, you hold the lock in between acquire and release, and you execute the code in the critical section. Okay, you can have two types of lock: spin lock and a blocking lock. Okay, we're gonna see that. So what's the idea here? Okay, the idea here is like, you can acquire the lock. Okay, you do the stuff and then you release the lock here. Okay, so if you do that, if you have thread 1 and thread 2, now you have the thread they started. Okay, and you see here you are in the middle of the critical section. Imagine there is a context switch. Okay, there's an interrupt and so on, and now it goes and thread 2 is go acquire the lock. But then thread 2 now is stuck because the lock is not free. So here it's not going to do anything. So it's going to yield the CPU, and then thread 1 is going to resume. So here it's going to put the balance and so on, and then release the lock. And here they can be after that. Actually here you can do the return and so on. Doesn't matter. But as soon as you release the lock, if there is an interrupt, that's fine. Here now acquire the lock will go through, and then now you can actually do your stuff and then release the lock. And by doing that, you're actually synchronizing the two processes. Okay. So how do you implement a spin lock? Well, you can think about it that way, a naive way, but it's wrong. Let me show you why. So okay, imagine you have a lock is actually a variable, and we set it to 0 at first. Acquire, what does it do? Say while it's false, okay, well, do a loop. Okay, you're going to be blocked. But as soon as this is equal to 1, as soon as it's going to be 0, okay, now you set it to 1. Okay, and then so here when you acquire the lock, meaning here, let me explain again. I think I said the wrong thing. If this is equal to 1, you're going to loop. And if it's equal to 1, it means somebody has already the lock. As soon as somebody has released the lock, whole lock is equal to 0, okay, then the lock, you turn the lock to 1. Okay, if I try to explain it again, maybe here when you're going to release the lock, you're going to set it to 0. 0 means, okay, you can go. And here, all the other ones are going to be stuck, right? So this looks like it works, right? But no. Why? Because here, you assume that, as you do that, this is atomic. It's not. Yeah, exactly. These instructions are not atomic. Meaning here, there can be a context switch in the middle. Again, you have a race condition. Wait a second. We have a race condition in something that we want to use to actually solve the race condition problem. Okay, we have a chicken and egg problem here. Okay, it doesn't work. So this is not really how it's going to be implemented. So here there's the hardware to the rescue. They have created a special instruction called test and set. So here, this is a CPU instruction. So again, CPU instructions, they are atomic by nature, right? So what does test and set does? It writes to a memory location, okay, and return its old value in a single indivisible step. Okay, so here basically it's like you write the value and you return the old address. Okay, it's kind of interesting here, but it doesn't do the job fully. But basically, the caller is responsible now for testing the operation has succeeded or not. if I were to have pseudocode, and again, this is pseudocode, right? I mean, this is a CPU instruction, right? There is no code for that. It's a CPU instruction. But if I were to have some pseudocode, it would work like this. You know, you have some kind of a flag, you turn the flag to true, and you return the old one. Okay? Why this is interesting? Because now you can have something like this. Okay? You can actually, you see here, you're gonna, it's gonna be the same for the lock and the release, but here you're gonna spin on this lock until the old value was actually 0. Right? You try to set it to 1 all the time, okay? But if the old value was 1, well, you are stuck. Okay, you have to spin. Okay, that's the idea. And at some point, if it's going to be 0, you're going to test it right away. I mean, you're going to test it and set it right away, and now you're going to exit that piece. Okay, so now it works. This is actually working. There's a little drawback here, okay? But again, it's working. But the drawback is, well, you're doing a while loop, meaning you have a process that is basically waiting and using CPU because you are executing this test and set instruction, right? But you are busy waiting. So you're wasting some CPU time, okay? This process could be sleeping, it would be better. And there's an unfair access to lock, right? Because imagine you have multiple threads, it's gonna be a race, okay? It's gonna be some kind of, you know, who is going to be the first one to actually test and set the lock. Here, there might not be any fairness, right? One thread can go long time without having the lock. So it's not great. There's another idea. Actually, this one may be the first idea that you might have. If you don't have the test and set, and actually it happens to not have it in old CPU instructions, you might do the following. You know, again, what is the problem here? The problem is when you are in the critical section, you might be interrupted. Okay, so you are a thread and you might be interrupted by the clock and you might lose the CPU time. So how about the following? You know, you don't want to be interrupted. Okay, you want to have the CPU just for yourself, at least for the time you execute the critical section. If it's the case, then so what you can do is like you can disable the interrupt. You know, oops, sorry. This is annoying. You disable the interrupt, you do your stuff, and then you enable the interrupt again. Okay, and actually this is gonna work, right? As soon as you disable the interrupt, the CPU is never gonna be interrupted. The thread is gonna have the CPU until it's released. Why it's bad? It's actually really bad. Okay, it's not a bad idea, but it's bad in practice. First of all, you don't want to give threads, especially user threads, the possibility to disable interrupts. Because what if they don't enable it again? Well, if they don't enable it again, your system freezes. There's nothing that is going to happen. There's not going to be any scheduling. Okay, no other thread is going to be executed. It's really bad. But also, if your critical section is long enough, you know, it's gonna delay events. Okay. So here, you know, if you have I/O, but also timer and so on, you know, if your critical section goes for like seconds before any interrupt, you know, there's going to be a lot of things that you're going to need. So it's not usually a good idea to do that. Those instructions aren't atomic. Disable interrupt, they are somehow atomic actually, because disable interrupt, it's the same thing as writing in a memory location to say, I mean, you're going to tell the PIC, remember the PIC from last week? You're going to tell the PIC, okay, please mask all the interrupts. So it's just like one instruction that says move this 0 to memory, for example. Okay, so yes, they are atomic in a way. So here, disable interrupt, it's some kind of atomic. And then, yeah, imagine never exiting the critical section. Yeah, you're right. I would say, no, this is a blue screen of death on Windows. Well, not even, right? It's really like, you know, it's even worse than the blue screen of death. So that's why usually we don't do that, or at least we don't give the opportunity to threads, user threads, to do these kind of things. The OS could do it though, and you will see it's going to be useful. So what's our lock implementation so far? We have two ideas, okay? Either spin locks or disable interrupts. They work, but they have drawbacks. What's a drawback? Spin locks waste CPU time and it's not fair. Disable interrupt, it's not good. It's going to delay events, especially if the critical section is locked. So what's the best approach? Well, the best approach is actually the following. This is how a good lock is implemented. And here, let me take you through this code. It's still going to be the same, meaning a lock is going to be a variable, either it's going to be 0. 0, the lock is free. 1, you are locking, basically, the lock is not free. And here you free the lock again by putting back to 0. Okay, so that doesn't change. What changed is like, well, now we have a queue. Why do we have a queue? To make sure that it's fair for every thread. So the idea is the following. If the lock is not free, we're going to put those threads in a queue. And when we're going to release the lock, we're going to give it to the next thread in the queue so that it's fair, right? Every thread will have eventually the lock. So we're going to achieve fairness like this. So how do we do it? Well, you can imagine the following. Like, let me not explain why we disable interact, but here, we're going to do that. Here, as soon as we have as soon as we want to enter the critical section, we do acquire. We are going to try to get the lock. Okay. If the lock is free, okay, you move there and you set up to 1. Okay, same as before. But if it's not, you're going to put yourself into a queue. Okay, so you can do that as you have the CPU. You yourself are going to put your own thread into the block queue. Okay, we saw that last week for process. Is exactly the same here. And then you're going to do what? You're going to say, okay, I'm going to block myself. Okay, I put myself into a queue and then I'm going to block myself. Okay, and blocking yourself, basically, you yield the CPU. You're going to say, okay, I cannot do anything. I'm going to yield the CPU, meaning the scheduler is going to schedule another process. And that's very important here. Okay. This thing, it's important. You're going to modify data structure. I mean, you're going to modify two data structure. One is the lock queue, and the other one is maybe the blocking queue that we saw last week. So here, as you do that, you don't want any other process to actually be able to do these kind of things. So what do? It's a critical section. Okay? Can you do a lock? Well, it's kind of weird, right? It's chicken and egg. We are trying to implement a lock, so you don't have a lock. So that's why here, we are going to disable the interrupt. Okay? Here, it's going to be fine to disable the interrupt because you are going to do something that you believe is going to be quick. Okay? This is not going to be too long. Okay? But you don't want to be interrupted because you don't want to have any problem. Okay? So here, you're going to disable the interrupt. Something important here, you might have a question. Okay? So of course, let's take the scenario. If the lock is free, okay, you disable the interrupt, you check the lock, okay, you get the lock. And then you re-enable the interrupt. You haven't been interrupted, nobody was tampering with the held value. You're fine. What if it's not? You disable the lock, you enter into a while loop, you enqueue yourself, nobody's interrupting you, and then you block yourself. And then what does it mean block yourself? I told you, right? Here, you basically yield the CPU. Meaning here, there's going to be another CPU that is going to take over. But wait a second. Another CPU is going to take over, but the interrupt are disabled. Who is going to enable them back? Well, actually, if you look at the code of thread block, and you can do it in Pintos, by the way. Well, this one actually is, every time this function is called, one of the invariant is that the interrupt are disabled. And the first thing it's going to do is like set back, it's going to do something with the queue here, okay, blocking the thing, and then right after that, re-enable the interrupts. Okay, and so same thing here with release, right? When you release, you disable the interrupt, you check the queue. If there is somebody in the queue, you're going to unblock you're going to unblock the next available thread. Okay. Doing that, by the way, does not call the scheduler. okay, you still have potentially the scheduling. So here, this is not the same as this one, right? Here we go through entirely, regardless of whether regardless. We're releasing the lock, so we're doing all of that. So you disable the interrupt, you unlock the next thread, and then you release the lock, and you re-enable the interrupts, and so on and so forth. Okay, this is annoying. Every time I click, sorry about that. Okay, so that's a good lock. Here, the lock is actually blocking when a process is actually blocked on, when it tries to acquire the lock and go into the critical section, it's not spinning like crazy. It's not wasting any CPU time. It's just falling asleep. That's exactly what I told you at the beginning. You fall asleep. Okay. Locks are usually, so that's a good idea, but locks are usually not implemented directly in the OS. What's implemented in the OS is called a semaphore, but you will see the idea is exactly the same, minus a twist. And maybe you have seen that actually in BO9, I'm not sure. But if you haven't seen it, well, you're going to see it in CSCC69 a lot. So what's a semaphore? It's the same idea. It's an abstract data type to provide mutual exclusion. Okay. Here, semaphores are integers that support two operations, P and V. Why those weird names? Well, that's because I think it's, what is it? I think it's Dutch. P means decrement, okay? And here it's usually going to be, it's the same as acquire the lock. Okay, you're going to try to enter into the critical section using P. P is going to decrement the semaphore, the integer. Okay. Sometimes P has other names. On Linux, actually, it's weight. On Pintos, it's going to be sema down. But you see also same weight in some books, I think. And of course, you have the release operation, which is V. And then now you're going to increment. You will see why I use increment. And you allow another thread to enter. Okay. On Linux, it's called signal. But on Pintos, it's called sema up. Semaphore safety property is the following. A semaphore value is always greater or equal than 0. Okay. What's this value? Well, okay. Maybe this is going to be more clear in a second. So with each semaphore, actually, there is a queue of awaiting thread. It's like my lock before, right? So when you do P, when P is called on a thread, if the semaphore is open, okay, the thread continue. If the semaphore is closed, you're blocked on a queue. When there is V, okay, when you release the semaphore, if a thread is waiting on the queue, you unblock the thread, okay? If no threads are waiting on the queue, the signal is still remembered for next time. Okay, so this is exactly the same as before. So using semaphore, I mean here, it's the same, right? P is going to be, acquire. So here you can do P. You can have other process, and actually now you can have multiple of them. You can have 2, 3, 4, n threads, and all of them are going to be blocked on P, right? And then, you put the balance and so on, you do all your stuff, and at some point you release the lock, and as soon as you release the lock, it's going to unlock the next one, but now in order, right? So it's going to be here, the red one, thread 2, because thread 2 was the first one to actually go in the queue, right? So there is fairness here. Maybe I should have this one first. There are two types of semaphores provided by OS. There is a binary semaphore called a mutex, and here really a binary semaphore is exactly the same as a lock, right? And controls access to a single resource. It's either there is one person going into the critical section, that's it. So that's why it's binary. But you have also the concept of a general semaphore, and that could be useful next week. What's the idea? We call that also a counting semaphore. You're going to say the following. When you initialize a semaphore, you're going to say, okay, I have 5 tickets, actually. Imagine, I have 5 keys, meaning 5 people, we have 5 tickets to go in the room. So here, you initialize a semaphore with the integer n, and then every time you do P, you consume one of these tickets. Okay, so here, if I start 5, one process is going to do P, the second one is going to do P, the third one is going to do P. And all of them are going to be able to actually go into the critical section. But at least, at most, n threads are going to be in the critical section. Meaning after 5, it's going to wait. Imagine, no more than 5 people in the room. The first 5 that come, they take the 5 ticket, and then once one person goes out, another person can go in, right? That looks like actually stores right now in the COVID with the COVID, right? There's only like n people that can be in the store. So yeah, so that's a general semaphore, and that's the kind of semaphore that you have actually in Pintos, on Linux, and so on. Okay, so that's why I was basically saying this idea of like here. I'm going to go back to that, but P is actually going to decrement. Okay, so you have a value 5, for example, it's going to decrement, and V is going to increment. But here, increment is not going to be more than the maximum. Okay, 5, and P here it's going to decrement, but if it's equal to 0, it's going to be blocked. Okay, right. So how do you implement it? Again, you know, it's going to look like the lock. Actually, it's going to be exact same thing minus some differences. What's the difference? Now it's not 0, 1. You have a value. Okay, and you have a value, and so when you do P again, you're going to decrement. Okay, but you decrement, but not if it's 0, because if it's 0, you're going to be blocked. If it's 0 means you don't have any ticket left. So we do the same thing, right? I mean, we disable the interrupt. If it's 0, you're gonna kind of wait. You put yourself in a queue, and you're gonna block yourself. Okay. As soon as you're unblocked, you take a ticket, and then you re-enable interrupt again. Here, when you disable when you release the ticket, you disable the interrupt, and then if it's empty, if there is somebody in the queue, you unblock that person, okay, and then you release the ticket and you re-enable the interrupt. That's exactly the same. The difference between the lock that we had before is this value can change, and you can initialize this value, of course, with init here. Okay. Shouldn't the struct also store the max value? Well, it is storing the max value here. It's this value thing. But here actually, you cannot go beyond 5. Why? Because you will never, I mean, you cannot do, by the way, you cannot do the V if you don't have the lock before. Okay, so yeah, so here, you cannot do V actually if you don't have a ticket, meaning it's not going to go over to the maximum. Okay, again, look at the way Pintos is implemented. Yeah, okay, Tony answered here, get passed by the user in init. General semaphores doesn't have the resource sharing problem. So again, we're going to see that next week, right? For example, for the bank example, you know, you only want one thread at a time, meaning you can use the counting semaphore, but you're gonna set the number of tickets to 1. Okay, meaning you're gonna get something we call a binary semaphore, right? So that's why here, I mean, sometimes the OS give you like 2 things, but you know, this is very generic so that you can use only this one, and you just set it to 1. And what you have here is mutual exclusion on a critical section, only one person at a time, right? Now, maybe your question is like, why is it interesting to have multiple people in the room? Okay, you have a weird critical section, right? You have a critical section that says, okay, you can have multiple people executing it, but only a certain number at a time. How is that useful? Well, let's talk about it next week, because that's what we're going to see next week. We're going to talk about all kind of problems using synchronization, and you will see some very interesting problems. They take advantage of this kind of thing. So what's the difference between a blocking lock and that you can have multiple processes at the same time? Yeah, exactly. That's the difference, right? So a lock, you can see it as a binary. Okay, again, I'm going to go back to that. Okay, if you have a binary semaphore, you basically have exactly the same as a lock. Okay, it's really the same. But again, the OS might call it a semaphore. And if you have a general semaphore, you know, you have something that is more kind of flexible, and that's going to be useful. Okay. All right. So again, that's the end of it. All of these are going to be useful for you because you're going to work on threads. You will have to synchronize them. You will have to be careful when you disable interrupts and re-enable interrupt and so on. So you will have fun with all of that for project 1. Start as soon as possible. It's not trivial. And again, it will be good by the end of the week if at least you get this interrupt business done. Okay, the TA is going to talk about that a little bit. And then if you have time, okay, look into the scheduling as well. Right? Yes, I'm going to post this lecture. So hopefully I have recorded this lecture twice. So it might be on Blackboard, but just to make sure, maybe I will post it on YouTube as well, so that it's there like the others. Okay. Any other question? Okay. If you have questions, again, I have office hours tomorrow, so feel free to pop in. Okay, thank you very much, and have a good day, and talk to you next week. Bye.